Let's start our class. This is our day 1 class, and this is about atmosphere. So I will say that you don't have to make any notes, because just understand the lecture, and this video will be available, and I will send you the PDF as well. So both will help you for the revision. Okay, very good. So see now, you see this atmosphere word. Actually, we are talking about the atmosphere which is surrounding the earth. Suppose you have the earth here, and there is envelope of air, and I'm saying air. So there is envelope of air, and in every this envelope we have classified into many parts, and we have to discuss mainly about the first part and the second part. So the first envelope is known as troposphere, and the second envelope is known as stratosphere. So we use only these two spheres for aviation. After that we don't use any sphere. After that also we have thermosphere, mesosphere, exosphere. We don't use that. So now when you have the surface, then you should know from the surface till how much height we have troposphere, and after that till how much height we have stratosphere. So from your 0 kilometer to your 11 kilometer we consider troposphere, and from 11 kilometer to 25 kilometer we consider stratosphere. So whenever you are finishing troposphere, and whenever you are starting stratosphere, then in between you have a line. This is imaginary line. It is kind of line which will separate troposphere and stratosphere. So suppose this is the line. Below that you have tropo, and above that you have strato. So this line is known as tropopause, because it is kind of pause. So the line is tropopause. Okay. So actually as a basic student, like without knowing science, if you will ask one question to a general person, like suppose this is the earth and here you have sun, and from this mean sea level you are going ahead towards the sun, then what will happen to the temperature? So mostly people will say that temperature will increase because you are going towards the sun. But this is not the reality. Why? Because temperature in the atmosphere depends on two major factors. So this temperature depends on pressure of the atmosphere, and this depends on density of the atmosphere. So when we are talking about pressure, then we should know what kind of pressure we are talking, because we have several types of pressure. For example, we have static pressure, we have dynamic pressure, we have total pressure, we have stagnation pressure, we have vacuum pressure, we have hydrostatic pressure. So these are the types of pressure. You can also say you have gauge pressure, and you can also say you have atmospheric pressure. So these are the types of pressures. So when I am saying that our temperature depends on pressure, my main motto is to talk about the hydrostatic pressure. And static pressure, dynamic pressure, slowly I will teach you in this course itself, I mean in aerodynamics itself. And so first thing, in our atmosphere, which pressure we bother? That is hydrostatic pressure. So first we should know something about hydrostatic pressure, and I will come to this point, but before that we will discuss the density part. What is the meaning of density? So see, if you talk about density, then density is roughly, you understand in this way, it is nothing but the crowd. Crowd means, but this crowd we have to talk about in a limited zone. Suppose you have this much zone and you have this much zone again. So in both the zone, suppose they are equal volume zone, and suppose here I am keeping only 3 particles or 3 people or 3 car or 3 bike or anything, 3 molecule, anything 3, and here I am keeping something like 30,000, same thing but 30,000 times. So in the same volume you can see here we have more crowd, so it means this is having more density. So how will you define the density? Density is nothing but how much mass is present in the given volume. So this is the symbol D. D is very popular symbol for density, but we use rho as the symbol of density. So this is rho is equal to mass by volume. So if you check the unit, mass is having unit kg. If you check the volume is having unit meter cube. So kg per meter cube became unit for density. Do we have any other unit for density? No. We use only this as a branded unit for density. And if you come to the unit, then for mass, we talk about SI unit only. For mass, unit must be kg. For volume, unit must be meter cube. And remaining things on the way I will be keep on teaching. For pressure, you should have volume Pascal, and for temperature, you should have Kelvin. So these are the popular units. And yeah, so now see, when we talk about density, then it has sense. That sense is like crowd. So now you come to the point of atmosphere again. Suppose this is Earth's surface, then it is like you have air present over the Earth's surface. So we have to analyze the air. What is air actually? So air is nothing but the combination of few important gases. So what are those gases? So if you talk about those gases, then you have nitrogen gas, and then you have oxygen gas, and you also have carbon dioxide. But these gases are, nitrogen is approximately 80%, oxygen is approximately 20%, and all the remaining gases, everything including carbon dioxide, ozone, whatever gases you know, all the gases are just in 1%. So that's why if you check, then our air is mainly nitrogen and oxygen, and in that we are breathing oxygen. So I mean, we are breathing everything, but body is accepting oxygen. So yeah, yes, actually I got your doubt. So entire atmosphere, wherever you will say that air is present, air will be present in this way. Okay, wherever you will go. Only thing is, near to the Earth's surface, you will be having, suppose near to the Earth's surface, you are taking one bucket of air. Just hypothetical situation, you cannot collect air into the bucket. Just imagine, near to the surface, if you are collecting one bucket of air, then in that number of nitrogens and number of oxygens will be more. But if the same bucket you will collect at the outer of the atmosphere, then numbers will not come. But whenever numbers will come, they will maintain this ratio. It's like yeah. So in case of nitrogen, you check, it is around 80%. In case of oxygen, it is around 20%. This rough data you should remember. I will give you the exact data also. And in the remaining 1%, you have CO2. And mostly people talk about CO2. More than CO2, we have argon gas present. Okay, more than CO2, we have argon gas present. So if you will make a list like this, then first you have nitrogen gas, then you have oxygen gas, then you have argon gas, and after that you have CO2 gas. Argon gas is a special type of gas. It is ideal gas. You say it is non-reactive gas. This gas will not react because if you can recall little bit from the 9th class chemistry, I will just show you something. In 9th class chemistry, if you remember, there was some periodic table, right? In the periodic table, you had the last group. In the last group, ideal gases, inert gases were present. Helium, right? Yeah. So argon is from that family. So it is actually neutral gas, or you say inert gas, or you say ideal gas. They don't, because it is not reacting. Now that is not our subject, why it is not reacting. But if someone will ask the question why it is not reacting, then you have to say, according to the chemistry, there is something called Octet Rule. According to Octet Rule, 8 electron must be there in your last shell. So that is the main thing. So we don't have to go into that, because no one will ask you that why argon is inert gas, because that is the chemistry, that is not the atmosphere. In atmosphere, we have to know that what are the gases are present and in what ratio they are present. Okay. Now see, we have to understand pressure and density variation in atmosphere. So we will target only troposphere and then stratosphere. After that, we will not target. So now I will not draw this kind of flat earth, because I will just consider this kind of earth, and above that I will consider, till here I have troposphere, and after that I have stratosphere. So this much is strato and this much is tropo. So see, because this is the earth surface, so you know that because of the gravity, heavier molecules will come closer to the earth. Heavier molecules will come closer to the earth, and lighter molecules will go away from the earth. So this gives you one idea. That idea is, when you will go up, your density will decrease. How can you feel this? Because you can see, near to the earth you have more molecules. Why do you have more molecules near to the earth? Because of the attraction force is heavy. Now how will you judge attraction force is heavy? Because for that there is something called Newton's law of attraction. If you have one mass m1, if you have another mass m2, so they will attract each other. So imagine one mass is your earth and one mass is the air molecule, so they will attract each other. So the force formula used to be G m1 m2 by r square. This formula you don't have to bother. I am just trying to say, based on the product of both the masses, we get our attraction force. So earth itself is a very heavy mass. So earth will try to attract everyone according to their weights. So molecules who are heavier, they will come closer to the earth. So that's why we have more density closer to the earth. If you will go away from the earth, you will be having less density. Why do you have less density away from the earth? Because see, you see here r square. Yeah, r square. R square means if you will go away, radius will increase, length will increase, gap will increase. So because of that, force will decrease. So attraction force will decrease. So molecules will be freely roaming in the external atmosphere. So more density is near to the earth. So here you understood one logic. When altitude is increasing, your density is decreasing. Okay. I am saying a word here, altitude. Very soon I will teach you there are 6 types of altitude, but currently altitude means height. There are 2 words I'll be using. In aerodynamics, we say altitude. Altitude means height. And in flight mechanics, I'll be using another word, attitude. Attitude means in what sense aircraft is right now. If this is the aircraft is like this. Maybe under some maneuvering, your aircraft will turn like this. So attitude changed. Attitude changed, not the altitude I'm saying. Okay. So 2 words we'll be using. Now, one thing you have to consider for grant. When altitude will increase, density will decrease. And logic is the attraction force. Okay. Now, density variation. Yes. Yes. Yes, definitely. No. You have to interrupt. Whatever is the intensity of the lecture, you just interrupt, because then only it is much better. Right. Yes, yes, yes. All situations, all situations, all situations, all situations, everywhere. Yeah, in all the atmospheric spheres. We are specializing troposphere and stratosphere, but this phenomena will keep on happening in thermosphere, mesosphere, exosphere, everywhere. Okay. So now I will change the page and then I will discuss the pressure variation. So in density variation, what is your key point? Key point is this: if altitude will increase, density will decrease. Okay, now I'll change the page. See, we are about to discuss pressure variation. As I have given you one rough idea, there are so many types of pressure. Out of that, we have to discuss hydrostatic pressure. Hydrostatic pressure. So actually, what is hydrostatic pressure? So actually it is because of the weight of the atmosphere. Now imagine one thing. Gases, if you will pack in any given volume, then that volume will be heavier. For example, you have LPG gas cylinder, what we use in our kitchen. So if there is no LPG gas, then your cylinder weight will be something else. But once you will fill the gas inside, then cylinder weight will be something else. It means you can say that gases are having their weight. Okay. Imagine this cylinder is made up of rubber. Okay, rubber. Rubber means just rubber. And imagine that it is not having weight. Like we can understand this in this way. Imagine a cylinder without weight. Skin is there, surface is there, boundary is there, but no weight. I mean, when there is gas, no gases. Once there is gas, then only there is weight. It is a hypothetical situation. Actually, in real life, we cannot develop this kind of cylinder without weight, because we have to use mass to construct the wall and the building of the cylinder. So definitely mass will come, weight will come. But just hypothetical situation, I have a cylinder. This is my LPG gas cylinder, and this cylinder is not having weight because it is empty. So now I am putting gas inside. So when you will put gas inside, it will be heavier. So when it is going to be heavier, then imagine if any person is sleeping below the cylinder, then what will happen? This person will experience heavier weight. So this person is experiencing the pressure here. That is because of the weight of the gas. If the gas will go out, then person will not experience any pressure. If you will fill the gas, then person will experience again. So weight will be experienced by the person. Question is, why the weight is experienced by the person? Gas is inside. So I am trying to say that gas is heavy. That is my only point. Gas is heavy. So how to link this concept in terms of atmosphere? So suppose this is our Earth surface, and this is our Earth surface, and here you have atmospheric air present. Everywhere you have atmospheric air present, everywhere. Now I am saying, just imagine this much column. You are imagining that there is imaginary cylinder. So don't you think there will be gas trapped in this cylinder when you will imagine any cylinder? So yes, so that much gas will be having weight. Yes, so that where the weight will act? The weight will act on the surface, right? So on the surface, whatever weight is acting. So there is one basic physics formula. Pressure is nothing but force by area. So your force is nothing but the weight of the gases present in the cylinder, and area is nothing but this cross section area. This cross section area. So that area. So when you simplify this, you get a formula. So actually how it is working, see, first of all you should know how to find out weight. So weight is nothing but mass into gravity. Then you should know which mass we are talking. We are talking about the mass which is trapped inside the cylinder. So mass is nothing but, you can see, mass is nothing but volume into density. Volume into density. Okay. Now this volume, which volume I am talking and which density I am talking? I was talking about the mass of the air. So definitely this density is the density of the air. What about the volume? Volume is that volume in which the air is trapped. So actually my air is trapped in that imaginary cylinder. So that is nothing but the volume of the cylinder what I have done there. So imagine I am drawing separate cylinder here, and I want to know how to find out volume of any given cylinder. So you can find out volume of any given cylinder with the help of area of the cylinder and height of the cylinder. Area means which area? Area means this cross section area. And if you will see from the top, this is nothing but a circle, right? So area of the circle is nothing but pi r square. So this area you can replace with pi r square, and this is the height. So this height, so pi r square h became the volume of the cylinder. It means this volume you can replace with pi r square h into rho into g. Or if you don't want to replace pi r square, just keep this symbol a, no problem in that. Okay, now come to the point. Are you able to find out weight? Yes. How? By using mg concept, then by using v rho g concept, then by using a into h into rho g concept. So substitute the value of weight here. So that is going to be a into rho into h into g divided by this area is there, area. Area will get cancelled. So you got rho gh. So you got hydrostatic pressure formula as rho gh. So with the help of this formula, you understand when you will go to more depth, this pressure will increase. What I mean, I will change the page. Suppose you have earth here like this, you have some kind of portion here, and in this portion water is filled. So this portion is water. Imagine this is ocean, any sea we can consider, and consider this is your sea bed and this is your earth surface. So suppose any person is in the boat and this person is jumping down, so it is diving now in the sea. So suppose person is reaching here. So because person is reaching here, so person is going into this much depth. So how much pressure will be experienced by the person? That pressure is known as hydrostatic pressure. That you can find out the formula rho gh. Now what is h? H is the depth. What is rho? Rho is the density. And what is g? G is the gravitational acceleration from the earth. So this is equal to, g is equal to 9.81 meter per second square. We will consider roughly. If this data is not given, then you can choose 10 meter per second square, but this will be rough data. Exact data will be this. Now see, what is this rho? So rho changes liquid to liquid. Currently I have considered water in my example, but imagine what if the same situation is with air. I will change the page. Suppose here you have earth, and till here air is present. So if you are standing here, it means you are in this much depth. So suppose this is the 500 kilometer. So after that you don't have a significant amount of air. So actually roughly we consider only till 500 kilometer we have atmosphere present. This is the rough data, okay? Only till 500 kilometer we consider our atmosphere is present. After that atmosphere, we say there is no atmosphere. Actually reality is everywhere in the universe atmosphere is present, little bit, but that is known as rarefied gas. So we don't talk about that. This is advanced field of gas dynamics. So main issue is your depth. If you are going into depth, your pressure will increase. It means because of the atmosphere, maximum pressure is on the mean sea level. That pressure we call as 1 atm pressure. And why do we use atm? Because it is because of atmosphere. Why do we use 1? Because that is the standard value. Okay, point is, if you have earth, then you have atmosphere present. So when you will go into the depth, pressure will increase. Just opposite, if you will go above, altitude will increase, so pressure will decrease. How will you judge this? because when you are going into depth, then only pressure is increasing. Because which pressure we are talking? We are talking rho gh. Okay, so you got the variations. You got two variation. In density, you got density variation. H will increase, density will decrease. Similar variation you got for pressure also. Height will increase, pressure will decrease. So you got your first equation, you got your second equation. Now these two variations are happening in all the atmosphere, in all these spheres. So based on this, if I'll ask rough question, this is the Earth surface, and here you have troposphere, and then here you have stratosphere, and when you are going up, your pressure will increase or pressure will decrease, or pressure will not change, or none. If I'll give you four options, then you should say that when we are going in upward direction, pressure will decrease in both the atmospheres. In troposphere also pressure will decrease, and in stratosphere also pressure will decrease. I can ask the same question. What will happen with the density? Actually, how do we write density symbol? You write S like this and you cover this completely. So it will be like this, some rough idea. Okay, so when you will go up, then density will also decrease. So in this case also density will decrease, and in this case also density will decrease. Now see, density variation simply I explained. To explain pressure variation, I took the help of hydrostatic law. Hydrostatic law, or you can say hydrostatic equation. That was nothing but P is equal to rho gh. Now I have to explain temperature variation. Temperature variation. So to understand temperature variation, you should know one more law. So there is one equation that is called ideal gas equation, that is known as P is equal to rho RT. You might have heard this equation in 9th class, 12th class, something in basic school. So this is known as ideal gas equation. So with the help of this equation, I can find out the temperature variation in both the spheres. Actually, in your first sphere, rho variation and pressure variation we know. In your second, rho variation and pressure variation we know. So we can find out the temperature variation. Okay, to find out temperature variation, in troposphere, you should apply P is equal to rho RT. So what is rho? Rho is the pressure. What is P? P is the pressure, rho is the density. What is R? R is known as gas constant. What is gas constant? Gas constant is actually R, and you can find out its value from R universal, that is universal gas constant, divided by molar mass. Molar mass. Actually, in our atmosphere, which gas is present? Air is present. What is the molar mass of the air? 29 mole per gram. 29. So yes, right. Okay, so for example, okay, see now, there are two ways to understand anything. One is the physical feel, like how will you understand physically? Suppose anyone is not knowing the mathematics, so like density variation you can understand physically. Near to the earth attraction is more, so density is more, and so density variation you can understand in every atmosphere. When you will go up, density will decrease. In same way, pressure also you can see, you are increasing in the altitude. It means you are going towards the level, towards the surface of the atmosphere. It means you are decreasing your depth. So if you are in less depth, suppose you are here, then more pressure, here less pressure, here more less pressure. So till this explanation I did not use formula. Now why do we have to use formula? Just now you will understand why to have the formula. Actually, to understand pressure variation you don't need formula. To understand density variation you don't need formula. But to understand temperature variation you need formula, because temperature depends on pressure and density. How? Temperature is proportional to pressure by density. I mean same formula I am writing like this. Okay, you can see this density I can send below, so it will look like pressure by density. Okay, so now see, you know, in both the atmospheres pressure is decreasing and density is also decreasing. So what does it mean? What will happen to the T? So for that we need formula. So see, pressure is also decreasing, so because of this decrement in pressure, temperature should decrease. Density is also decreasing, so because of this decrement, temperature should increase. But in case of troposphere, this pressure decrement effect is dominating. It means temperature decrement effect is dominating as compared to the density. For example, suppose there is something called 100 and there is something called suppose 99. Imagine this is the value of Z. Suppose you can see, if I will decrease 100 alone, then Z value will decrease. For example, if I'll make this 99 by 99, if I'll make this 98 by 99, if I'll make this 95 by 99, so you can see this numerator is decreasing, because of that Z will decrease. Just opposite, if I will decrease this also, this value also if I will decrease, then this should increase. But actually in real practice they sent, I mean all the scientist people, they sent, there is something called sounding rocket. They sent sounding rocket in the atmosphere. So you have Earth, so they sent sounding rocket. Earlier India was not having sounding rocket, so we used to borrow from Russia and USA. Now we have our own sounding rockets. What is the meaning of sounding rockets? We will launch sounding rocket, and sounding rocket will go up in the sky, and till where the sounding rocket will go, it will collect the data of nearby properties like pressure, temperature, volume, this kind of density. This kind of data will be calculated by sounding rocket, and this data will be sent back to us. So according to the data, we analyzed that decrement in pressure, I am talking about the troposphere, decrement in the pressure was very faster as compared to decrement in density. So if you will check out, temperature is proportional to pressure by density. Pressure was decreasing very faster as compared to the density was decreasing. Both are decreasing, but this guy is decreasing very bigger. So because of that, this effect is dominating. So temperature will be decreasing in troposphere because pressure is decreasing faster. So from here you got the result, and your result is in troposphere, when you go up, your pressure decreases, your density also decreases, and temperature also decreases. Why temperature is decreasing? So for that you should write like this: temperature decreases because pressure decreases faster than density decreases. So this was about the troposphere. So mainly we have to bother about these three variations. These two variations are constant kind of variation in all the sphere, but this variation will not always be decreasing in all the atmospheres. So currently you got troposphere. So in troposphere you have certain numericals, and to solve those numericals you have certain formulas. So now I have to know, in your syllabus whether you have to deal with numericals or you only have to deal with theory. Okay, then fine. Okay, then fine. So this is the theory. Temperature will decrease in troposphere. So you don't have to focus more on the mathematical part now. I mean, whatever I have explained mathematically, P is equal to those things, you don't have to bother about that. You just go with the logic like this. Okay, both are decreasing, all the three are decreasing in troposphere. Then we will go for second one. So in second one, what happens? In second one, again, temperature variation in stratosphere. Actually, what happens there? Again, pressure is proportional to temperature is proportional to pressure by density. Now here what happens? Pressure decreases, because of that temperature should decrease, but density also decreases, because of that temperature should increase. So see the beauty of this is atmosphere. Pressure decrement and density decrement gives decrement and increment in temperature, and beauty is this decrement and this increment is exactly same. That's why temperature is constant. So temperature is constant from 11 kilometer to 25 kilometer. We have stratosphere, and in that stratosphere, if you will go up, suppose this is the Earth's surface, and then here till here you have troposphere, and then you have stratosphere. So 0 to 11, 11 to 25. So from here your temperature value will keep on decreasing, but after that it will be constant. So you should also remember this point. At mean sea level, we consider our temperature as 288 Kelvin, and when you will go to 11, it will decrease. After that, constant. Yeah. So this is the logic in troposphere and stratosphere. Now we will start discussion about, there is something called international standard atmosphere. So what is that? So your next heading is international standard atmosphere. This is very important topic of your exam. So what is this? Actually, see, when you talk about entire globe, so we have several countries, and atmosphere will not vary. I mean, atmosphere is not same above every country. Like atmosphere over the America is something else, atmosphere over the London something else, over the India something else. So if you will construct any aircraft, if you design any aircraft according to the atmosphere of India, then this will be suitable only in India. But as you know, one aircraft has to fly across the continent. It will go to different countries. So it has to face different atmospheric challenges. So because of that, we don't work on any particular atmosphere. What do? We take the data, we collect the data from every country. How do you collect the data? Using sounding rockets. Using sounding rockets, we collect the data, and that data we use as average data. I mean, with the help of that data, we used to find out average data, and that data we say that okay, now we don't have this kind of atmosphere. It is just a theoretical knowledge. We say that okay, in real life we will not consider our real atmosphere. We will consider this data as our atmosphere. So this is not the real atmosphere, it is just a data. So that's why we consider this as the standard value for the atmosphere for all countries. So international standard atmosphere is nothing but a hypothetical set of values, and these values we have got with the help of these sounding rockets, and we give this value to all the countries. Like with the help of this value only everyone will consider, and everyone will fly, and everything will do in aviation. So international standard atmosphere is not a real atmosphere. It is just the set of some values. What kind of values? The values what we are getting from the sounding rockets, and you have to make the average of all the values. So now next important logic is, we have to talk about altitude. So actually we have three types of altitude. One is geometric altitude. One is absolute, and one is geopotential. So this geometric altitude is the altitude measured from the surface. Suppose this is the Earth surface. Suppose here you have any satellite. So from the Earth surface, what is the altitude? That will be geometric altitude. And what is absolute altitude? You add the radius also in this, then you will be getting center. Means from the center, when altitude is measured, then that is known as absolute. So absolute altitude is nothing but radius plus this thing, geometric altitude. Now what is geopotential altitude? So see, in both the cases, either you talk about geometric altitude or you talk about absolute altitude. When we go up, then we go far away from the center. We are going away. Then this gravitational acceleration will decrease when we go up. So in case of geometric altitude and in case of absolute altitude, whenever you go up, your G value decreases. But geopotential altitude is again a hypothetical altitude. According to this altitude, you measure any location, but when you reach to that location, your G value will be exactly same as the Earth on the surface. So in case of geopotential altitude, your G value will be same what we got on the surface. So what is geopotential altitude? It is just a hypothetical altitude. Okay. Can we find out geopotential altitude with geometric altitude? Yes, we have formula for that. But as you are saying that you don't have to bother about the formula, so no problem. Only concept based we will do. So this is very key idea about the atmosphere. Now we have to talk about stability of the atmosphere. Your atmosphere is stable or not? Stability of atmosphere. So what does it mean? So see, stability of atmosphere. So to understand this stability of atmosphere, you should understand that on the globe, at every position, you have atmosphere present. But every position is not at equal distance from the sun. So first problem is every position is not at equal distance from the sun. Second problem is every location is not equally high. For example, Chennai is at zero mean sea level, because you can see if you go to Marina Beach, it will be just zero because you don't have any height. You are just at the mean sea level. You're just standing in front of sea, so you don't have any altitude. But if you will go to just nearby Bangalore is 900 meter above the sea level. That's why Bangalore is having very good weather, even as compared to Dehradun. Even Dehradun is in hilly areas, but Bangalore is having much better atmosphere than Dehradun. Even Dehradun is at altitude. What is my point here? My point is two things are responsible for the atmosphere. One thing is how far you are from the sun. Next thing is your altitude. Altitude means at how much height the city is established. So see, main thing is why atmosphere will get disturbed. Atmosphere will get disturbed. Why atmosphere is not same everywhere? That is because of the sunlight. You have earth here and you have sun here. Just now I explained like every city will not be at same altitude and at same distance. So imagine here, just imagine this condition. Here more heat is going, more heat. And just imagine here less heat is going, less heat. Why here more heat, why here less heat? It is because of on the way we have some disturbed atmosphere, right? Ozone layer, somewhere thick, somewhere thin. So what will happen? Because of the heat, here air will get more temperature. Here air will get less temperature. So more temperature air will be having more energy. So this temperature air will start going somewhere else. And when this temperature air will leave the position, then here vacuum will come. So because of that, other airs will go and jump, will occupy that place. So this is the way air will come on the earth. Air, the blowing air, not the still air. Air blow. Why air is blowing on the earth? Because of the temperature difference. Everywhere temperature is different. That's why air is blowing. Sometimes you will experience that in our atmosphere everything is there, air is there, oxygen is there, but air is not blowing. So when this kind of atmosphere you will see mostly this kind of atmosphere you will see when you have almost equal temperature everywhere. So take the example of Chennai. Maybe actually mostly air will blow in Chennai, but some days when almost temperature is same everywhere, mostly in summer season, so because temperature is almost same everywhere, so you don't have change in temperature. That's why gases will not shift, and air you will experience when gases will shift. So here we understood the stability of the atmosphere. Now point is, we have understood the disturbance of the atmosphere. We have not understood the stability of the atmosphere. So let's understand what is the meaning of stability of the atmosphere. So for that, imagine your atmosphere is made up of these air molecules. Okay, I am drawing 4 sets of molecules, and now suppose here you have Earth's surface. So imagine because of something, some heat transfer or some kind of vehicle or something, this much atmosphere is getting less density. So what will happen? This entire atmosphere will go up. Why this entire atmosphere will go up? Because according to physics basic rule, less dense people will go up. For example, oil is having less density, it will float over the water, right? So oil is having less density, it will float over the water. So this is the main logic. Oil, less density people will float up, they will go up. So imagine this atmosphere is having less density, so this atmosphere will go up. So if the atmosphere is stable, then this atmosphere will come back also. If the atmosphere is not stable, then you have two choices: unstable and neutral. Neutral means till where this atmosphere is going, finally suppose here, then here only this will stay. So this is called neutral condition. And unstable condition means your atmosphere will keep on going. It will start from here, it will not stop anywhere on the way, it will keep on going. So actually this kind of atmosphere is not good for us, because when imagine any aircraft is coming, so this aircraft will not experience uniform atmosphere. So in atmosphere we'll be having different type of issues. So for example turbulence, and there are lot more. So that is the aircraft phenomena, we will not go into that. Our main topic is atmosphere. So this is the very basic idea about the atmosphere. So majorly you have to bother about two things. What is your troposphere, what is your stratosphere, and once troposphere, stratosphere is done, then you should know there is something called lapse rate. What is lapse rate? Lapse rate is nothing but with how much lapse rate, with how much rate your temperature is decreasing in troposphere. Because this is the earth, this is the troposphere, this is the stratosphere. So imagine here you have value 288, but when you will cover 11 kilometer, your value will decrease, temperature value will decrease. So it will be 216.5 Kelvin. Actually you can see the value decreased. So this value have decreased in 11 kilometers. So actually your value of lapse rate is 6.5 Kelvin per kilometer. It means what? When you will travel 1 kilometer up, 6.5 Kelvin temperature will get minus from this. When you will go 2 kilometer up, then from the next temperature again you decrease this much value. When you go 3 kilometer up, then from the next answer you decrease again 6.5 value. So this is how temperature will keep on decreasing. So this is about the lapse rate. So again you have to remember only this thing, like lapse rate for troposphere is 6.5 Kelvin per kilometer, and in case of stratosphere it is 0, because in stratosphere there is no temperature decrement. And there are some formulas, and there are some like density variation, pressure variation. Those things we don't have to discuss, as you said, like numericals are not there, so we will not work out the numericals. This theory is sufficient. Yeah, so actually in today's class whatever we have discussed, in that we don't have much theory. Right now we will go for, there are three other types of attitudes. There is something called temperature attitude, pressure attitude, density attitude. So what is that? So let's understand, for example, what is pressure altitude. Now, yes. Yes. Hmm. Mm-hmm. Okay, then no problem. I will go a little bit slow because I have to go according to your speed. So you can control me. You can tell me, or you can stop me. We can discuss something because I have to know that what kind of speed is comfortable. If this topic is the last topic of the atmosphere. Yeah. So because you have to be comfortable, you should. You have to tell me like. You want to discuss anything or something, then slowly I will come to know like what kind of speed is comfortable for you. Okay, so you see pressure altitude. What is pressure altitude? So actually in earth surface, suppose you are going at 5 km height, then in real life at 5 km height you will be having certain pressure. So suppose that pressure is 0.8 Pascal. Just imagine this pressure is 0.8 Pascal. This is not the right value. It is just for example. Okay. So what is pressure altitude? So just now I said there is something called ISA, International Standard Atmosphere. What you have to do? You have to open ISA chart. In ISA chart, because this ISA value is the average value from all the atmosphere around all the country, I mean everywhere. So definitely everywhere at 5 km you don't have same pressure. Maybe if this data I am telling just above the India, maybe above the America at 5 km you don't have same pressure. So that's why in ISA table at 5 km you will not be having same pressure. Okay, so you go to pressure table and you check out where 0.8 Pascal is written. So wherever 0.8 Pascal is written, in front of that what height is written. So that height will be your pressure altitude. It means in real life 0.8 Pascal we are getting at 5 km, but in ISA table the same pressure we will be getting at certain other altitude. So that new altitude will be your pressure altitude. I will repeat again with the help of temperature altitude. Now, yeah, tell me. Pressure, right. For example, suppose this is India and suppose this is USA. So suppose I am going 3 km above. So I'll be having a particular temperature here. So suppose, just an example, this temperature is 270 Kelvin. I'm not sure about the data, just example purpose I'm taking. But one thing is sure, same 270 Kelvin will not be above USA. This thing is very sure. This, if you are going same 3 km, of course this temperature is not will be equal to the same temperature. So now I will not consider this part. I just want to understand what is called temperature altitude. So I will just consider any one country. So I'm considering India. So suppose, again this example is just an example. So above the India, if you will go 3 km, just imagine your temperature is 270 Kelvin in real life. Okay, but what is your temperature altitude? So temperature altitude is the altitude. Which kind of altitude? Just now you remember we had three types of altitude: geometrical, absolute, and geopotential. So actually temperature altitude is the geopotential altitude, but it is given in ISA table. So you have to open your ISA table and you have to go to temperature column. In temperature column you check out where this much temperature of 270 Kelvin is given. So in front of 2 Kelvin temperature, what is the height mentioned? So that height will not match with 3 km height. That will be some other height. That height is known as temperature altitude. In same way you have density altitude. Density altitude exactly same. What is density altitude? Again same. See, this is the earth surface. Go to a particular altitude. Any altitude you can choose. Suppose you are going some 8 kilometer. So after going to 8 kilometer, you will be having certain altitude density here. Just imagine your density is 1. Just imagine 1 kg per meter cube. So go to the ISA table. Then in ISA table, you go to the density column. In the density column, all the density will be listed. You check out where is 1. So suppose here is 1. So in front of 1 height will be mentioned. So that height will be your density altitude. Okay, so that's all over. Now what we have learnt about troposphere, height of troposphere, temperature, pressure and density variation in the troposphere. In same way, stratosphere, temperature, pressure and density variation in stratosphere. Then we saw about ISA. Then we saw our 3 types of altitude: geometrical, absolute and geopotential. Then we saw pressure altitude, temperature altitude and density altitude. So that's all. Only this much we used to study in atmosphere.